Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Hani Farhana binti Zaman, and today I'm going to present my thesis, which is the synthesis and physicochemical characterization of cinnamic acid intercalated into layer double hydroxide by self-assembly method. First, I'm going to explain about LDH. LDH or layered double hydroxide are also known as the anionic clay or hydrotalcide-like systems. It was known as hydrotalcide due to its water content, hydro, and talcides. LDH has a benefit over other layer materials, which is the composition and metal anion combination that it may form. And it also has a unique quality, including enhanced biocompatibility, high chemical stability, and pH-dependent solubility. For the problem statement, first, even though cinnamic acid has a widespread use in pharmaceutical, cosmetic, and dye industry, but the high concentration of cinnamic acid can cause serious health problems. Even in research from Gunia Krisak et al. 2018, the cinnamic acid derivatives such as octinoxide, amyloside, and autocrylines are contact and photocontact allergens. And meanwhile, sinoside has been reported as a photocontact allergen on rare occasions. So the significance of the study is first, instead of directly using cinnamic acid, we can intercalate it into LDH, so it will be much safer and can be potentially commercialized. And cinnamic acid can also be commercialized as a UV protection in cosmetic product without causing allergic reaction to the consumer. Okay, then the objective of my thesis is first to synthesize the zinc aluminum layered double hydroxide by self-assembly method. Second, to synthesize the cinnamic acid zinc aluminum layered double hydroxide by self-assembly method. And lastly, to determine the physicochemical properties of the synthesized material by PSRD, FTIR, CHNS laser, and accelerated surface area and porosimetry with PET analysis. Okay, next is the methodology. There's a three main part in the methodology, which is first is the preparation of the cinnamic acid with different concentration. For this study, I have prepared 4 samples with different concentration of cinnamic acid, which is 0.05 mol, 0.1 mol, 0.2 moles, and 0.4 moles of cinnamic acid. Okay, next is the synthesis of zinc layered hydroxide. 125 ml of the prepared zinc aluminum LDHR2 was mixed with 50 ml of cinnamic acid that has been prepared before. Then 2 mol NaOH was dropwisely added until the pH of the solution is 7.5. The sample was then aged in the oil by shaker for 18 hours at 70 degrees Celsius. So the sample was cooled and centrifuged for 7 minutes to remove the water excess and iron content in the sample. After the centrifugations, the sample were then dried in an oven at 70 degrees Celsius. The samples then were finely ground and kept in the sample vial for characterization. And the third part is the physicochemical characterization. For this study, I have used 4 analytical instruments, which is PSRD, FTIR, CHNS, and BET analysis. Next is the result and discussion for PSRD. And as shown in graph in figure 1, we can see that D003 peak for zinc aluminum LDH host has a basal spacing of 9 angstrom. So, and as we can see from 4 samples of zinc aluminum cinnamic acid, the D003 peak has shifted to the more left side or the lower regions. So the basal spacing for zinc aluminum cinnamic acid with 0.4 mol is 18.9 angstrom, 0.2 mol is 18.7 angstrom, 0.1 mol is 19.3 angstrom, and 0.05 mol is 19.9 angstrom. So all the sample value are much larger than the basal spacing of 9 angstrom from the zinc aluminum LDH host. So the increase of basal spacing indicate that there is entrapment and replacement of anion has occurred. The shifted of D003 peak is due to the cinnamic acid has successfully intercalated into the interlayer space of zinc aluminum LDH and then replacing the nitrate position to form zinc aluminum cinnamic acid nanocomposite and reducing the crystallinity of the LDH. And as the concentration of cinnamic acid increase, the amount of nitrate present may decrease until all the cinnamic ion completely replace the nitrate ions. Then, FTIR was used to determine the co-intercalation of the cinnamic acid and the nitrate ion in the zinc aluminum LDH host. So figure 2 has shown the comparison between the zinc aluminum LDH host with cinnamic acid and intercalated zinc aluminum cinnamic acid. So zinc aluminum has shown a strong absorption band at 1363, suggested that the presence of nitrate in the zinc aluminum LDH, which we cannot see in the cinnamic acid spectra, but in the zinc aluminum cinnamic acid spectra, there's a significant peak at around 1363 cm-1, which indicate the existence of the NO stretching and the incomplete intercalation of the cinnamic acid. But as we can see from the zinc aluminum cinnamic acid sample, the nitrate peak decreased as the quantity of the cinnamic acid increased. For the cinnamic acid functional group, we can see the existence of absorption band at 3200 and 2600 cm -1. This is show the presence of an OH group that overlap with CH absorptions. There's also bands at 1676 that show C-double-O stretching, 1622.7 that show C-double-C stretching, and 1277 that show the CO group. Then we can see the same goes with the zinc aluminum cinnamic acid that show bands at 1648 cm -1 for stretching of the C-double-C group. Okay, next is the CHNS analysis. Table 2 show the percentage weight over weight of carbon, hydrogen, and nitrogen for the LDH host and zinc aluminum cinnamic acid samples. So the percentage of carbon has increased as the concentration of intercalated cinnamic acid increased. The zinc aluminum LDH host has 0.122% of carbon, and compared to 0.05 mole of cinnamic acid, it increased to 6.78%. The nitrogen has decreased from 3.51% in zinc aluminum to 2.94% in 0.05 mole of cinnamic acid. This suggesting that there is inclusion of cinnamic acid anion into the interlayer of zinc aluminum LDH and the negation of some nitrate anion from the zinc aluminum LDH intergallery. This has supported the result from the PSRD that show there is co-intercalation of nitrate and cinnamic acid anion. And as the concentration of cinnamic acid increase, the percentage of carbon also increase, which show more cinnamic acid intercalated into the zinc aluminum LDH. And we can see that the percentage intercalation of cinnamic acid also increase as the concentration of cinnamic acid increase from 6.98% in 0.05 mole cinnamic acid to 28.84% in 0.4 mole cinnamic acid. And lastly, the PET analysis. And according to the INTERCALATED classification, the graphene is a type 4 isotope. Figure 3 shows the nitrogen adsorption-desorption isotope of zinc aluminum and zinc aluminum cinnamic acid compound, respectively. Zinc aluminum shows slow adsorbent absorption at relatively pressure range of 0.0 to 0.45 p over p naught and optical uptake at 21 cm3 per grams, whereas zinc aluminum cinnamic acid intercalation has shown rapid adsorption at relatively pressure range of 0.0 to 0.2 and then followed up by a slow uptake from 0.25 to 0.9 and optimum adsorption at 2.1 cm3 per grams. So when compared the zinc aluminum cinnamic acid, the desorption branch is much narrower in zinc aluminum LDH. As indicated in table 4.3, there is increase in pore size and pore volume from zinc aluminum LDH to zinc aluminum cinnamic acid. This suggests that there is intercalation of cinnamic acid into the zinc aluminum LDH interlayer. However, we can see that surface area does not differ much in this case. 3.8411 meter cube per gram in zinc aluminum LDH and 2.3327 meter cube when cinnamic acid was loaded at loading percentage of 20.52%. So in conclusion, the cinnamic acid has successfully integrated into the zinc aluminum LDH interlayer by self-assembly methods, and the correlation and the confirmation for each result are as shown in FTIR, PSRD, CHNS, and PET analysis. And we can observe that the vessel spacing has increased from 9 angstrom in zinc aluminum LDH to 19.9, 19.3, 18.7, and 18.9 angstrom in 0.05 mole, 0.1 mole, 0.2 moles, and 0.4 mole respectively. Then, the percentage loading has shown an increase as the concentration of the cinnamic acid increased, and at the lowest concentration, 0.05 mole, the percent loading is only 6.98%, and at 0.4 mole concentration, it's increased to 28.84%. There is still room for improvement that can be done in the future. For example, the cinnamic acid concentration can be changed or modified to result in a considerably larger percentage of cinnamic acid loading into the LDH host. And second, further study on the release of cinnamic acid should be done to explore the suitability of zinc aluminum LDH as host for controlled release of cinnamic acid. That's all from me. Thank you.